because the distinction between the two, in my view, is becoming more and more artificial, and the distance between the two is getting smaller and smaller, because psychiatry is getting more and more involved in brain mechanisms, brain structures that cause behavioral problems and cause other problems in thinking and emotions. And the neurologists are also discovering, on the other hand, that they cannot cut out what we call psychiatric issues in their practice. And so, with time, my expectation is, and especially after what we will talk about today, that we will use the same mechanisms, the same structures, and the same spaces to understand problems that today we call neurological problems and those that we call psychiatric problems. So, based on this view of neuropsychiatry, the mind is thought to be a product of brain activity. And the brain is like a black box that receives input from the environment. And based on those input, it develops an image of the world in which we live. Now, if it creates a good image of the world in which we live, an adaptive image of the world in which we live, then we thrive. But if it creates an image that is not in keeping with what is around us, then we struggle a little bit. And therefore, mental illness comes from that understanding. And so this forms the template around which we build artificial intelligence. And for a long time, more than 60 years, scientists have been trying to understand how the brain works, this black box, how it works, in order to make us adaptive and thrive. In order to do this, some decided to start developing algorithms that are derived from statistics, mathematics, and data science to try and understand, if you give certain input into this black box, what kinds of outputs do you expect to get? And so they modeled this on how the brain, how they thought and how they continue to think the brain works. So in 1943, these two fellows developed an algorithm that they figured it mimics how a neuron operates. Because a neuron gets input, a neuron gives output. And then there are multiple layers of neurons that ultimately give even more complex outputs. And so this algorithm that they developed, they called it a perceptron, and we'll be speaking about this a little bit more today. But just in general, if for nothing else, if we don't remember anything else from today, to think about what AI, why is it called artificial intelligence? Because it mimics human brain function in two main ways. One is that those neural networks that are built to solve complex problems are modeled on actual neurons and how they function, using the perceptrons and so on. But the second thing is that AI is designed to mimic human intelligence, so that it does things that one might think an intelligent human being would do things in that way. And we will see a little bit about that shortly. So formally speaking, artificial intelligence is a field of computing to begin with. It started with computing, as I have just shown you, with programs or algorithms that are developed with the ability to learn, and I should put learn in quotes because I'm going to explain what that means, and reason, again in quotes, like humans. So the ultimate goal is to develop algorithm that, when given input the same way humans get input from our sensory system, gives output that is similar to that of an intelligent human. And a subset of AI known as machine learning is about developing those algorithms that can learn without you going at every step and giving it input. So you give one input, it looks at the data, and it learns from the structures in that data without additional human input. And deep learning is a further subset that involves algorithms like what I just talked about, artificial neural networks, and I'll go into that a little bit more, and they learn from vast amounts of data, so what we call big data. Now, this is a perceptron on the right. It looks very complex with those symbols as squiggles and X's and so on. But the X represents the input. Whatever the input is, usually it's data of some kind. And then the W, right next to the X, are weights that are given to the different inputs based on importance. You can decide what importance you want to assign each of the weights. And so you might give one weight, one input more importance than another, and so on and so forth. And so there are different relative weights. And then they come to the transfer function that sums up those inputs multiplied by the weights, and then takes it into the activation function, which is the decision point. Do we fire or do we just stay in our current state? So 0 or 1, that is the language that computers understand. So if it has reached a certain threshold, it fires. If it doesn't reach that threshold, it doesn't fire, and that input doesn't result in anything. And that is with one neuron, artificial neuron. And so it mimics the actual human neuron here, which receives input, again the x's on the left, and then gives output, the y's on the other end. And in between, there are certain operations, including weighting of those inputs by importance. So that's just a summary of how the neuron inspires artificial neurons. And so when we talk about artificial neural networks, we look at it down here. And in the beginning, I have simplified it by saying there's input, then there are these weights and so on, and then there's output. But then in artificial neural networks, the middle layers, which are called the hidden layers, can be many. They can be as many as 100 different connections. They can be hundreds, thousands of different connections, depending on the neural network that you're building and the inputs and the operations that you'd like to happen. So as a result of that, what happens in the hidden layers is not often apparent to the people giving input and getting output. But it is still a series of operations and calculations and algorithms doing their thing until you get an output. The theory is that, does it really matter what exactly is happening in the hidden layers if the output is accurate? So that is what the computer scientists say. It doesn't really matter. As long as the output is consistently accurate given inputs, and we do this during training of the algorithm, then you don't want to concern yourself too much with what exactly is happening inside those hidden layers. So that in general is a summary of what we do as artificial intelligence. So what is AI? AI, as I said, are programs use huge volumes of data to classify things based on similarity and differences, to predict future outcomes based on previous data, and to recommend interventions based on previous outcomes. That's really a summary of what AI does. It is designed to mimic human thinking, human speech, human appearance, human movements, and so on. And it is able to perform calculations with vast amounts of data at incredible speeds. And therefore, it's very good at number crunching and data processing, things that we would struggle with. And finally, it helps to deliver on very human needs. So the solutions that this AI is designed to solve are very, very human, for human problems that we encounter, but that will take us a lot of time and resources if we were just to say that let humans do it themselves. What is it not? Because I think it is important for us to also clarify what AI is not. And it will surprise you to note that, in my view, AI is not intelligent in the classical sense that you would think. Having given you that long description of what AI is, I think you would agree with me that it is not intelligent. It is a series of mathematical calculations which have been designed by very clever people to solve very real human problems. All right? So it is not intelligent in the sense that we measure intelligence among humans. And when we talk about training of an AI model, we are talking about humans who give it input, and then they look at the output, and then they see how accurate is the output. And if it is very far from the expected accurate output, they go back at each of the stages and change those weights, the W's. They change the values of those weights, and then they come back and look at it again until the output approximates what is expected in the training phase. Then they put it through the test data, and they check whether the outputs remain accurate. And that is the process of training. So remember, there's a human intervening in that process. AI is not sentient. So AI doesn't know that it exists. Because, as I said, it is a series of algorithms and calculations and numbers and operations acting on an input. So it doesn't know it exists. And with the current AI as we know it, it's unlikely that it will reach a place where it will say, I know I exist. But it is designed to behave in a manner that is similar to humans. so that when a human interacts with it, they would think that this is a sentient creature that I'm interacting with. But it is not. Learning, when you talk about machine learning, is about tweaking the algorithm so as to improve the output and make it more accurate. It doesn't mean that it will sit here in a class like this and think like a human, make decisions like a human. There are way too many variables that humans interact with in order to make decisions that AI doesn't have access to. It is not autonomous, again, in the sense of that it can, start doing things in its own interest. It does things based on the instructions we give it. It gives outputs based on the inputs that we put in. So those are the things that AI is not. And so then now, how do we apply this in neuropsychiatry? How do we apply the knowledge about what AI can do and what it cannot do in neuropsychiatry? And there are four things. There are four areas where AI would become extremely important for us in mental health. The first one is in classification, because we are in the business of classifying disease, of classifying outcomes, of classifying medications, of classifying interventions. So that is the first thing that AI would be extremely useful, because using millions of data points, millions of presentations, it can help with that. The second thing, importantly, is prediction. If you show up in my clinic, stooped over, 50 years old, you are trembling, and your speech is in a certain way, and there are certain things you are saying. If I break those into variables and enter them into an algorithm, it might be able to tell me whether you will be alive 1 year from now. It might be able to tell me what I should do in order to increase your chances of being alive 1 year from now. So prediction. Recommendations. So again, using data of outcomes from millions of other people with conditions similar to yours, we could then make a recommendation and say, based on this person's presentation, these are the things that are likely to have the best outcomes. And finally, in automated care, and I will say something about that towards the end, and it's all about generative AI. So in classification, as we all know, we argue a lot in conferences like this about whether schizophrenia is one entity or it's a collection of entities presenting with some common symptoms, but then different trajectories. Is depression one illness, or is it a collection of illnesses that converge on final common pathways that include the symptoms that we see patients presenting with? AI can answer those questions much more easily than we can, because with access to millions and millions of cases, it would be able to look into that data set and find how many groups have similarities among them and segregate them. And then using your intelligence as a human, you would be able to say, why is this group having similar individuals? And how is it different from the other groups that this AI algorithm has suggested? And that would be extremely helpful in classification. I usually say that if you give me full information about yourself and I know everything about where you came from, how you were conceived, where you were born, what you have been eating since you were born, if I have a machine capable of getting all that data and I meet you today, I can tell you exactly where you will be 6 hours from now. Unfortunately, we never ever have that kind of information. And that's what brings us to prediction. So with huge amounts of data from people who look like you, who behave like you, who have symptoms like you, and we know their outcomes, based on that data, we can tell you with a degree of confidence how you are going to respond if we perform a certain intervention on you. And that is the second use case for AI. Recommendations, as I have said, again, knowing everything about your illness, about where you're coming from, about your other conditions that you're carrying, the system can make recommendations and say people like this often respond in this way when given these groups of medication or this kind of psychotherapy or changes like this in their environment. And it would be able to make those recommendations, and you as a clinician would then make a choice based on recommendations that are evidence-based. The final case is in automated care. And think about ChatGPT, which is also a system made up of algorithms. What does the algorithm do? The algorithm, once you give in an input, it calculates the probability, what output has the greatest probability of being accurate given the input you have given it. So if you ask ChatGPT, what is 3 plus 7? ChatGPT does not calculate 3 plus 7. It doesn't know how to calculate. ChatGPT goes into its huge library of data and algorithms and says, when somebody asks, what is 3 plus 4? What is the commonest next word? And it finds 7 as the commonest next one. And it will give you the answer 7. But that's why it is inaccurate sometimes. If you ask it certain calculations, it will give you an inaccurate response because it doesn't calculate. It looks through data and says, given this string that has been inserted here, what is the most accurate output based on the data that I have been exposed to? So that is important for us to understand. So it is very good in mimicking conversation because there are millions of conversations that have been stored in online databases that it has been trained on. So if you come to it and attempt to have a conversation, chances are every word you're going to say, somebody has said it somewhere and received tons of answers. And so that is what it will be operating on in deciding what should be the next response. And so you have to remember that it just uses probability to determine the most appropriate next output, whether it's a word, a pixel, a sound, a movement, a picture, and so on, given a prompt. And this is why there's a huge emerging field today of prompt engineering, where people find out if you want a certain output, what should you ask ChatGPT? And people have a growth industry on that. There are now books that have hundreds of suggestions of what you should ask it if you want a certain kind of output. And it's all maths, it's all statistics, it's all probability. So it cannot think or reason if you understand that that is how it is working. It cannot think or reason in the classical sense that humans think and reason. And so what does the future look like? In my view, the future is that we will attempt to collect more and more data from healthy individuals before they get sick and probably have it in a secure database somewhere that is accessible to the user, but also accessible to service providers, including clinicians, including doctors, and so on, with permission, of course. So this data will be streaming in, and it will be streaming in from hundreds of thousands of millions of people. And so when you become unwell as a patient, you might have access to this system, and you might say, I have a headache. And there are hundreds of millions of people exactly like you who have had headaches and have had certain interventions done, and it will get advice for you based on that. Or it might tell you your chances of survival are greater if you go to hospital now and see this kind of specialist rather than buying Panadol. And so the system can make a tentative diagnosis based on the fact that it has collected lots and lots of data from you and from people who look like you, and then you have given it input with a symptom, and it might make a diagnosis and recommend. Now, if the patient goes to hospital, if you decide that I need to go to hospital, it is probable that the hospital would then have access to that database, including your data with permission. And so saves a lot of time in asking you whether you have been exposed to smoke, pollution, whether you have been exposed to noise, whether there is a stressor in your environment, because that data is likely to be in the system. And all we input is additional complaints that you have. And the system will then classify the condition that you have, make recommendations to the clinicians for potential care, and the clinician will make a decision about what to do with you. So what's the entire point of everything I have said for the past few minutes is that the future expert in mental health has absolutely no choice but to start getting acquainted with AI, machine learning, and data science, because that will become the thing that is inside a black box that often tells you the options you have in an intervention. And that if you ignore it, your outcomes are more likely to be worse than for those that use that system. And so by natural selection alone, we will start weeding out those of us who are not able to understand AI or use data or understand the outputs. So this is not a threat. as the president said, alisema ni gapi? Yeah, so that's the thing. The gap between psychiatry and neuroscience has narrowed, as I have said. I hope I have convinced you that brain function inspired AI. And I hope I have convinced you as well that AI uses what we know about brain function to design algorithms that address new problems today. And that due to increasing computing power and huge amounts of data that are available to us, AI is able to solve problems in neuropsychiatry faster and with more accuracy. And we must deliberately leverage AI to improve how we diagnose and treat new neuropsychiatric disorders. Thank you very much.